Welcome back to the deep dive. Today we are opening up a technical report that, well, it honestly feels like a direct challenge to the current orthodoxy in large language model scaling.
It really does. We're talking about the LongCat-Flash paper.
Exactly. Specifically, their 560 billion parameter mixture of experts model.
You know, it's a fascinating document. Usually when you see a model pushing past that half-trillion parameter mark, the whole conversation immediately pivots to, the immense cost and the latency.
Penalties, yeah. But LongCat-Flash is claiming to have broken that linear relationship between model size and how slow it is to get an answer.
The numbers they're putting out are aggressive.
Oh, they are. Training on 20 trillion tokens in just 30 days. But the metric that really matters for anyone trying to actually use this thing, the inference throughput, is over 100 tokens per second.
Per user. On H800 hardware?
That's just not typical behavior for a 560B model.
Not at all. I mean, that's a performance you'd expect from a model maybe an order of magnitude smaller. To get that with this parameter count, it implies they haven't just thrown more GPUs at it.
No, they've done something fundamental. They've re-engineered the whole pipeline.
The execution pipeline, the routing logic, everything.
Exactly. And that is our mission for this deep dive. We're going to strip away any of the marketing fluff and look strictly at the engineering. We need to unpack these zero computation experts, the shortcut connected Mo, and the very specific stability fixes they use.
The ones that stop the gradients from just exploding at this scale.
Right. And we should probably get into the infrastructure layer, too. Some of those kernel optimizations are really quite novel.
Absolutely. So where should we start? The architecture.
Let's start there. The core idea seems to be this efficiency by design, and it kicks off with the zero computation experts. Now, standard MOE routing is pretty well understood. You have N experts, you route to the top K. How does LongCat-Flash diverge?
So, in a standard setup, every single path you route a token down incurs a computational cost, right?
Right, you're hitting a feed-forward network.
Exactly. LongCat-Flash introduces a set of, let's call them Zello experts, that exist alongside the standard Zello experts. The critical distinction is that these Zello experts are identity functions.
Identity functions. So they just pass the input, $6 directly to the output without doing anything to it.
Correct. No matrix multiplication, no nonlinearity, just pure pass-through. It effectively allows the model to dynamically decide not to compute on certain tokens.
Which creates a variable computational budget per token.
Exactly that. And this is a huge deal. In a dense model, every token costs the same FLOPs.
Yeah.
In a standard MOE, it's roughly the same too. But here, the report says the active parameters fluctuate between, 18.6 billion and 31.3 billion.
All depending on how hard the model thinks the token is.
Yes. That variance suggests it's actually learning a difficulty heuristic.
But hold on, this raises a control problem, doesn't it? If you give a neural network a zero-cost path, the path of least resistance is to route everything there and, do nothing. How do they stop the model from just collapsing into laziness?
That's the clever part. They implemented a PID controller for the expert bias.
A PID controller, like from industrial engineering.
Exactly that. It's a clever application of control theory. Instead of just a static loss for load balancing, they actively modulate the expert bias term using a proportional integral derivative loop. So the bias isn't really learned via gradient descent in the usual way.
So what is it doing?
It's adjusting the bias to force the average number of activated FFN experts, the thinking experts, to converge to a target, keyed. The PID controller makes sure the mean stays on target, but, and this is the key, it lets the standard deviation float.
Ah, I see. So it enforces a budget over a whole batch, but it gives the model the freedom, token by token, to use more compute on a hard one and less on an easy one, as long as it all balances out.
Precisely. And a crucial detail is that they exclude the zero computation experts from these bias updates. If you start biasing the identity experts, you create this feedback loop that just destabilizes everything. They only regulate the FFN experts.
That makes a ton of sense. You're forcing it to allocate its thinking capacity efficiently. Okay, let's move to the second big piece of architecture. The shortcut connected MOE, or SCO-MOE. This seems to be targeting the communication bottleneck.
Right. When you're scaling to tens of thousands of accelerators, that all-to-all communication, the dispatching combine phase, that becomes your bottleneck. Your compute cores are just sitting there stalled, waiting for data.
And the usual trick is to try to overlap the computation with the communication.
You do. But what LongCat-Flash does is change the order of the pipeline to make that overlap window as big as possible. They call it a single batch overlap pipeline.
So how does the data flow work there?
Well, they introduce a cross-layer shortcut. Essentially, they decouple the dense FFN operations from the MOE operations across different layers. So the dense FFN from the preceding block, let's say layer L-1.
Is running at the same time as the communication for the MOE layer in the current block, layer L.
Yes. By reordering the execution like that, they hugely expand the window where communication and computation are happening at the same time. The report shows it's quality neutral, doesn't hurt perplexity, but it gives you this massive improvement in throughput.
It effectively hides the MOE routing latency behind the dense computation from the step before.
It just turns that communication penalty into a background process.
Let's shift gears to training stability. Because we know that as models get this deep and this wide, managing variance becomes, well, it becomes everything.
It's the primary adversary, and this is critical for a 560B model. They call out two specific sources of variance misalignment. The first one is in the multi-head latent attention, or MLA.
That's the part with the low-rank compression, correct?
Yes. In MLA, you have these compressed latent vectors. The problem is that the variance of your query and key vectors scales with their smaller compressed dimension, but the rotary embedding part scales with the full model dimension.
And that mismatch would cause the attention scores to just be completely dominated by the rotary embeddings right at the start.
Exactly. It skews the whole distribution. So to fix it, they introduce these specific scaling factors, alpha Q and alpha KV, that basically align the low-rank parts with the full model dimension. It just normalizes everything.
And they apply a similar kind of logic to the experts themselves.
They do. See, as you add more and more experts, you're fine-graining the model, but you're also diluting the gating probability. Each expert gets a smaller slice of the pie.
Which leads to a reduction in the output variance. The signal just vanishes.
So they compensate. They use a scaling factor, gamma, which is just the square root of the segmentation factor. So if they split an expert into more pieces, they scale the output up to keep the variance consistent.
It really seems like the theme here is just maintaining constant variance no matter what.
It's the golden rule of deep learning stability, isn't it? If variance grows, you explode. If it shrinks, you vanish.
Speaking of gradients, let's talk about the optimizer. I found this detail about the atom epsilon parameter surprisingly specific. They set it to 1e16.
This is a great in-the-trenches kind of insight. Standard epsilon in atom is, what, 1e8? It's just there for numerical stability. But at this scale, they found that the root mean square of the gradients was actually dropping below 1e8.
So the stability term was bigger than the actual gradient signal. It was drowning it out?
Exactly. The adaptive learning rate in atom just stops working because the denominator is all epsilon and not the actual gradient history. They had to lower it to 1e16 to make sure the optimizer was actually responding to the data.
That just implies the gradient signal in these massive, sparse models is incredibly subtle.
It is. And it requires extreme precision, which I guess brings us to router stability and the greedy norm ratio, true dollars.
Right. This is about the conflict between the load balancing loss and the actual language modeling loss.
It's a real tension. The LM loss wants to specialize experts, make the distribution spiky. The load balancing loss wants to spread everything out, make it uniform. If the load balancing gradients are too strong, you just wash out all the specialization.
So they monitor the ratio of the gradient norms.
Yes. They track Schraller to make sure the load balancing part is just a gentle regularizer, not something that's overpowering the main goal.
And one final stability point, the hidden Z loss. This is for the outlier activation problem.
Correct. We see this in large transformers, these huge activation spikes in the final layers that cause loss in stability. So they add a small penalty on the log sum x of the absolute values of the final layer output. It just suppresses those massive outliers.
It stops one neuron from screaming louder than the rest of the network.
Essentially, yes. Keeps the dynamic range sane.
So let's move on to what you get for all this engineering, the agentic capabilities. The report makes this really strong claim that LongCat-Flash is a non-thinking model that excels at agentic tasks.
And that's a really significant distinction right now. We see so much focus on, system 2 reasoning models, chain of thought models that think before they answer. LongCat-Flash is optimizing for system 1 fast, intuitive execution.
But they claim performance on par with those reasoning models. How are they bridging that gap?
It all comes down to the data strategy, specifically this mid-training phase where they shifted the data mixture to be 70% STEM and code. But the real kicker is their synthetic data framework.
The multi-agent synthesis framework.
Yes. They figured that difficulty in these agentic tasks really comes from 3 dimensions: information processing, toolset complexity, and user interaction. So they built agents to simulate each one.
The toolset agent generates the environment.
It generates mock tools,
Yeah.
creating this dense graph of APIs. I mean, we're talking about tasks where the model has to pick from over 30 available tools on average. Then the instruction agent creates tasks that require navigating that complex graph.
And the user profile agent.
That one is designed to simulate friction with the user. Real users are stubborn or vague, or they don't want to give you information. This agent simulates that, forcing the model to learn strategic questioning.
Which feeds directly into their proprietary benchmark, VitaBench.
And VitaBench is interesting because it specifically tests this high cardinality tool use, with scenarios that go for over 60 interaction rounds. LongCat-Flash scored 24.30, which is ahead of its peers. It suggests that by training on these synthetic high-friction scenarios, the model just really rest. It sort of memorizes the reasoning patterns.
It internalizes the logic into its weights instead of having to derive it at inference time with a long chain of thought.
Which brings us right back to the efficiency argument. If you can get the same agentic outcome with one fast-forward pass instead of a slow, iterative reasoning chain, well, the economic implications are massive.
Speaking of economics, we have to cover the infrastructure optimizations. Getting to 100 TPS isn't just about the model, it's about the kernel implementation.
And the report puts a huge emphasis on determinism. In a distributed system, this big, silent data corruption, SDC, is a total nightmare. One bit flip can poison an entire training run.
And they mentioned recomputing sensitive operators during idle phases?
Yes. They literally use the idle gaps in the pipeline to rerun things like the flash attention gradient calculation just to verify bitwise consistency.
That's an incredible level of paranoia, but I guess it's necessary when the training run costs millions.
It paid off. They reported 98.48% availability. But for inference, the real standout optimization is this thing called SwapAb.
A kernel optimization for the MoE GMM, right?
It is. See, in MoE inference, you get really irregular batch sizes. Different experts get different numbers of tokens. Standard libraries assume uniform batches or they pad the data, which just wastes compute.
And they usually expect the weight matrix on the right-hand side.
Correct. SwapAb flips it. It treats the weights as left-hand matrices and the activations as right-hand egg. This transformation lets them handle the irregular batches way more naturally without padding, and it maximizes tensor core use.
It's a custom matrix multiply for the ragged arrays you get from MoE routing.
Exactly. And when you combine that with speculative decoding using multi-token prediction.
Ah, right, the MTP draft model. They use a single dense layer for the MTP heads, not a full MoE layer.
Yes, because a full MoE would be way too heavy for a draft. By using a single dense layer, they keep the parameter overhead tiny, like 1.4%, but they still get an acceptance rate over 90%.
Over 90% is an incredibly high acceptance rate. It implies that the dense head is really well aligned with the full sparse model.
It validates all those training stability measures we talked about. The throttle is so coherent that a simplified head can accurately predict what the full sparse mixture will do.
So to summarize the whole technical landscape here, we have a model that gets insane throughput from zero computation experts and clever pipelining. It stays stable at 560 B parameters through very careful variance alignment and tiny optimizer tweaks like that 116 epsilon. And it delivers top-tier agentic capability by basically memorizing tool use patterns from synthetic data.
And it does it all at a reported cost of 70 cents per million output tokens. That figure is the real enabler here. It moves these complex agentic workflows from technically possible but way too expensive to commercially viable.
It really challenges the assumption that smart agents have to be slow thinkers. LongCat-Flash suggests that intuition, or a statistical approximation of it, can be engineered to run at 100 tokens per second.
It completely blurs the line. Is it retrieval? Intuition? Reasoning? If the model can navigate an 80-node tool graph instantly because it's seen millions of variations, is that functionally different from reasoning through it? For the end user and the latency budget, the answer is probably no.
A compelling argument for efficiency being its own form of intelligence. For listeners who want to dig into the CU-Day kernels for SwapAb or the PID controller logic, the full technical report is up on ArtChef.
I would highly recommend checking the appendix for the ablation studies on the load balancing loss. The trade-offs they map out there are very, very instructive.
That does it for this deep dive into LongCat-Flash. We'll see you on the next one.